On August 14th, Alibaba released a model that created a very strange comparison. On one side, Claude Opus 4.6 Max, one of Anthropic's flagship models. On the other side, a model with just 27 billion parameters, open weights, Apache 2.0, and small enough to run on a single consumer GPU. The model is Qwen 3.8 27B, and according to Qwen's own benchmark table, it doesn't just get close to Opus 4.6 on some coding tasks, it actually beats it. On SWE-bench Pro, Qwen scores 61.7. Opus 4.6 Max scores 53.4. That is an 8.3 point advantage for a model you can literally download and run on your own machine. So naturally, the internet started calling this thing something like Opus at home. But that creates a much more interesting question. Can you actually get Opus level performance on a gaming GPU? And if you can, what GPU do you need? Because the answer is much more complicated than just download the 27B model. First, we need to understand exactly what Alibaba released. Qwen 3.8 27B is a dense model. That word matters. This is not a giant mixture of experts model where only a small fraction of the parameters activate for each token. All 27 billion parameters participate during inference, and yet the model is still small enough that quantized versions can fit into consumer hardware. The recommended 4-bit versions need roughly 17 to 19 gigabytes of combined memory. So immediately, something like an RTX 3090 or RTX 4090 with 24 gigabytes of VRAM becomes very interesting. You can put essentially the entire model on one GPU. No API, no subscription, no sending your code to somebody else's server. The weights are sitting on your computer, and the model is Apache 2.0 licensed. But before we talk about hardware, we need to answer the obvious question. Is it actually as good as Opus? Because one benchmark is not enough. Let's look at the strange shape of Qwen's benchmark table. SWE-bench Pro is probably the number getting the most attention. It tests software engineering on real repositories. Qwen 3.8 27B scores 61.7. Opus 4.6 Max scores 53.4. Qwen wins. Then there is OSWorld verified. This tests whether an AI can actually operate a computer. Qwen scores 80.3. Opus scores 72.7. Another surprisingly large win. On AndroidWorld, which tests mobile device interaction, Qwen scores 81.9 compared with 62 for Opus. On IFBench, Qwen scores 79.5 against 60.5, and even on LiveCodeBench version 6, Qwen is slightly ahead, 90.3 versus 88.8. If you only looked at these numbers, you could make a ridiculous sounding conclusion. A free 27 billion parameter model running on your desk just beat Claude Opus. But keep reading the table, because this is where the story changes. On Terminal Bench 2.1, Qwen scores 73, Opus scores 78.2, on GPQA Diamond, Qwen gets 89.2, Opus gets 91.3, and then we get to humanity's last exam. Qwen 30.8, Opus 40. That is not a tiny difference anymore. So Qwen 3.8 is not simply Claude Opus, but local. The performance profile is much more interesting than that. For agentic coding, instruction following, computer use, and several multimodal tasks, this tiny local model can compete with, and sometimes beat, the Opus 4.6 numbers. But when the task becomes extremely difficult, closed book reasoning, Opus still pulls ahead. And there is another important detail. Opus 4.6 is not even Anthropic's newest Opus anymore. Anthropic released Opus 4.7 in April, Opus 4.8 in May, and Opus 5 in July. So when you hear someone say, Qwen 3.8 beats Claude Opus, that sentence needs a giant asterisk. It beats Opus 4.6 Max on specific benchmarks. That is still extremely impressive. It is just not the same thing as saying this 27B model is better than Anthropic's current frontier model. And surprisingly, I think that makes Qwen more interesting, not less, because we are comparing a 27B model that runs locally with something that was frontier class only months ago. So how does a 27B model get this good without becoming impossible to run? Part of the answer is hidden inside its architecture. Qwen 3.8 has 64 language model layers, but they are not all normal full attention layers. The pattern looks like this: 3 gated DeltaNet layers, then 1 gated attention layer. Repeat that 16 times. So out of 64 layers, only 16 use the full attention mechanism. The other 48 use gated DeltaNet. And this matters enormously for local inference. Traditional attention needs to remember keys and values from previous tokens. That memory is stored in the KV cache. As your context gets longer, the cache gets larger. And if every layer uses full attention, long context can absolutely destroy your memory budget. Qwen avoids a lot of that growth by using DeltaNet layers for most of the network. Think about it like this. Normal attention keeps a giant box containing old receipts so it can go back and inspect them. DeltaNet is closer to maintaining a compressed running state. You lose some of the simplicity of perfect direct lookup, but your memory does not explode in the same way. Then every fourth layer gets full attention again. That hybrid design is one reason Qwen can offer a native context window of 262,144 tokens while remaining surprisingly practical. And Qwen says the context can even be extended toward 1 million tokens. Now, 1 million tokens does not mean you should open a million token coding session on a 24 gigabyte GPU tomorrow. The KV cache still exists. Context still consumes memory, and extended context is not the same thing as native context. But architecturally, this model is clearly designed around one problem. How do we make long context agents practical without requiring data center hardware? Which finally brings us to the question most people actually care about. Can your GPU run it? Let's start with the easy answer. If you have 24 gigabytes of VRAM, you are in the good zone. The recommended 4-bit build needs roughly 17 to 19 gigabytes of memory. That means cards like the RTX 3090 and 4090 have enough room not only for the weights, but also some breathing space for context, runtime buffers, and other overhead. There are also 6-bit builds around the low 20 gigabyte range if you want to push quality higher. For most people with 24 gigabytes though, 4-bit is probably the obvious starting point. This is where the phrase Opus performance on your GPU starts feeling surprisingly real. Not universal Opus performance, but a genuinely powerful coding and agent model running completely locally. Now let's drop to 16 gigabytes. This is where things get uncomfortable. A standard 4-bit Qwen quant can already be around 17 gigabytes, and that is before you give the model meaningful context. So a 16 gigabyte GPU is not really a comfortable 4-bit Qwen 3.8 machine. You can use smaller IQ4 variants. You can use 3-bit dynamic quants. You can quantize the KV cache, or you can offload part of the model into system RAM. But now every decision becomes a trade-off: quality, context, speed. One of them has to move. For a 16 gigabyte GPU, I would think of 3-bit as a safer practical tier rather than trying to force the recommended 4-bit build into almost zero remaining memory. And this is important because fitting the model file is not the same thing as running the model well. If the weights consume almost every megabyte of VRAM, your context still needs somewhere to live. At 12 gigabytes, things get even more aggressive. 2-bit versions can get into roughly the 11 to 13 gigabyte memory range. You can also use CPU offload. Technically, yes, the model can run, but this is where I would stop using the phrase Opus on your GPU. Extreme quantization changes the quality equation, and moving weights between system memory and GPU memory can destroy token generation speed. There is a massive difference between I made Qwen 3.8 launch on my laptop and I can use Qwen 3.8 as a productive coding agent. Those are not the same achievement, and at 8 gigabytes, this difference becomes even more important. There are extremely compressed builds that can technically get very small. But once you combine aggressive quantization, tiny remaining context space, and memory offloading, you are no longer demonstrating the experience that made this model interesting in the first place. So yes, people will absolutely run Qwen 3.8 on hardware that looks impossible. That is what the local A community does. But if you actually want to use this model every day, 24 gigabytes is the clean target. 16 is workable with compromises. 12 is experimental territory. There is one more feature that could make the local experience much faster. Multi-token prediction. Qwen 3.8 was trained with an MTP head. Normally, an autoregressive language model generates one token, then another, and for every token, the GPU has to move the model weights through memory again. That is why local LLM inference is often limited more by memory bandwidth than raw compute. MTP tries to change the equation. Instead of predicting only one token, an extra prediction mechanism drafts multiple future tokens. The main model then verifies them. If several guesses are correct, multiple tokens can effectively be accepted together. Fewer full passes, more throughput. And because the main model still verifies the draft, this is not the same thing as simply making the model smaller. The interesting part is that Qwen was actually trained with this capability. But there is a catch. Do not expect a magic universal 3x faster button. The speed up depends on your runtime, your hardware, your context length, your sampling settings, and even the kind of prompt you are running. If the draft predictions are frequently wrong, the advantage collapses. But if your runtime supports Qwen's MTP properly, it is absolutely something you should test, especially if you already have the entire model sitting inside VRAM. Actually running the model is also much easier than it sounds. Unsloth already provides GGUF versions across multiple quantization levels, and llama.cpp can pull and serve those models directly. For a 24GB GPU, start with a 4-bit GGUF. If you are on 16GB, start lower and leave room for context instead of trying to win a screenshot competition showing that the model technically loaded. If you want image understanding as well, remember that the GGUF setup also needs the vision projector. Because Qwen 3.8 27B is not just a text model. It has a vision encoder and was evaluated on image and computer use tasks too, so the same local model can potentially read your code, look at a broken interface, reason about the screenshot, and then modify the software behind it. That combination may be more important than any single benchmark number, but there is one final benchmark caveat we need to talk about. The comparison table comes from Qwen. This is Qwen evaluating Qwen. That does not automatically make the numbers wrong. And importantly, the 50.4 SWE-bench Pro score for Opus 4.6 Max is the officially reported Opus result. Anthropic's own published material also confirms several of the Opus numbers used in these comparisons. But this still is not the same thing as a completely independent third party running every model through exactly the same environment and reproducing every result. So I would treat these scores as strong evidence that Qwen 3.8 27B is unusually capable, not mathematical proof that it has somehow become Claude Opus. And that leaves us with the part I think actually matters. 6 months ago, Opus class capability meant renting access to a massive proprietary model in somebody else's data center. Now we have a 27 billion parameter model that can beat Opus 4.6 on SWE-bench Pro, beat it on OSWorld, run locally, see images, handle more than 262,000 tokens natively, and fit into roughly 17 to 19 gigabytes at 4-bit precision. That does not make Claude obsolete. It does not make frontier APIs pointless. And it definitely does not mean every $500 GPU has an Opus hiding inside it. But the gap between local model and frontier model is getting weirdly small in very specific workloads, especially coding, especially agents, and especially computer use. So maybe the real question is not, is Qwen 3.8 better than Claude Opus? The better question is, if a 27B model running on a graphics card under your desk is already this close, what exactly will local AI mean 1 year from now?